Assalamualaikum and good day. My name is Muhammad Amirul Iman. So for our group 8, we have chosen for this project our material to be magnesium copper alloy. So in this slide, there will be an explanation on the properties, phase diagram, microstructure, or application, and also other things that related to the magnesium copper alloy.
Physical properties of MgCu. The composite of MgCu is known to be in a lightweight. It is excellent in resisting corrosion. MgCu have a range of density from 2.6 to 2.8 gram per centimeter cubic. The strength of copper magnesium wire is developed by cold drawing. This results in the highest strength in the smallest cross-section, which is 80 millimeter squared. Copper magnesium alloys cannot be hardened by heat treatment. They may be stress relieved between 150 and 200 degrees Celsius and fully annealed between 400 to 500 degrees Celsius. Melting point is approximately 500 degrees Celsius. It also has good conductivity and good solderability.
While the mechanical properties of MgCu alloy is that it have good resistance toward atmospheric and marine corrosion, it is stress relieved at 140 to 200 degrees Celsius and fully annealed between 400 to 500 degrees Celsius. It has a tensile strength between 470 to 520 Newton per millimeter squared, a yield strength of 430 Newton per millimeter squared, and it can also be elongated to 3 to 10% of its original length.
Next is application of magnesium copper alloy. As you can see on the slide, magnesium copper are usually found in electrical components such as wires and cable. This is because of magnesium copper alloy that has a properties like high strength, good conductivity, good solderability, and also resistant to corrosion. These properties make it suitable to be used in the electrical components or appliances. So these are the application usually used in the industry: conductor wire, connector wire, pins, automotive switches and relays, terminals, catenary cables, and also automobile wire harnesses. This is the phase diagram for magnesium copper. So as we can see, the magnesium copper phase diagram has a lot of phases. So from our phase diagram, we can observe the more obvious thing. The first one is intermediate point. So how do we find our intermediate point? We can see from our solid solution. So here we can see that we have a CuFCC and MgCu2, and here we have MgCu2 and Mg2Cu. So the first intermediate point for in our phase diagram is here, MgCu2. So MgCu2 occurs at a high temperature with the presence of extra copper. So as the MgCu2 cool down, it's fully convert at around 380 degrees Celsius or around 653 Kelvin. So the next one is we can see from our solid solution MgCu2 plus Mg2Cu, and the other one is MgHCP and Mg2Cu. So from this we know that our intermediate point is Mg2Cu. So for Mg2Cu, it is formed in two steps. The first one is nucleation, and the other one is growth. So it undergo both of these steps in order to form the Mg2Cu. So the forming started from around 841 Kelvin.
Generally, isothermal reaction happens at eutectic point. For MgCu, there are three eutectic points present as shown in the phase diagram. The first one is at 22% Mg and 1008 Kelvin. The second one is at 59% Mg and at 823 Kelvin, while the third one is at 84% Mg and at 760 Kelvin. The microstructure of eustatic point at 84% Mg at 760 Kelvin is as follows. At point 1, the microstructure is filled with liquid L. Upon reaching the solidus line at point 2, you can start to see that the lamella of MgHCP plus Mg2Cu starts to form, but the majority of the microstructure is still filled with liquid. And finally, at point 3, the microstructure is filled with lamella MgHCP plus Mg2Cu. The graph temperature K against time was plotted to show the cooling curve for eustatic point. As you can see, at 760 Kelvin, this is where the eustatic point is. The temperature stays constant even though the time is increasing. This is where the isothermal reaction takes place.
Solidification at 4% copper. Alpha solid solution. Magnesium copper alloy are cooled from a liquid state from a high temperature. As the temperature approaches the liquid line, it started to form copper precipitates. After temperature dropped from 1350 Kelvin, it continues until it reaches approximately 1100 Kelvin. It reaches the region of liquid plus copper. When temperature dropped below 1100 Kelvin, copper austenite started to form. After it cools down approximately below 710 Kelvin, MgCu2 will be forming in copper austenite. Microstructure at 4% copper. At point 1, approximately 1350 Kelvin, the microstructure is totally liquid. The microstructure of point 2 is at the region of liquid and copper. And at point 3, approximately 1008 Kelvin, the microstructure is copper austenite. Cooling down at point 4, approximately 600 Kelvin, MgCu2 will be forming in copper austenite. The cooling curve or 4% copper. As we can see, the line shows that the temperature is being melted, and then the copper reaches to 1325 Kelvin at the liquid line in the liquid region. Then it continues to melt until it reaches the liquid plus Cu region to the solidus line. Then the temperature becomes constant at the L plus Cu region. It then continues to cool down to Cu plus MgCu2 region. The composition at 700 Kelvin, composition of CuFCC is 97% copper with 3% magnesium. Composition of MgCu2 is 66% copper and 34% magnesium. At the MgCu2, it is 3.226%, and the MCU is 96.774%.
Moving on is the solidification at 30% Cu, or we can say as a hypereutatic composition. So the first thing is from the phase diagram we can see that magnesium copper alloy is cooled down from a high temperature in a liquid state. So as it cools down approaching the liquid line, MgCu2 started to form in the microstructure. So around 1060 Kelvin. So after it passes the liquidus line, so the microstructure it will have liquid and magnesium copper 2 phase. So as it cools down again, approaching the solidus line, the copper solid is started to form in the microstructure. So when it is on the solidus line, a lamellar structure of copper FCC and MgCu2 can be seen alongside the MgCu2. So then it cools down again past the solidus line around 1008 Kelvin. So in the microstructure, we can see there will be a lamellar structure. Lamellar structure consists of copper and MgCu2 and with a eutectic of MgCu2. So for us to better see our explanation on the solidification, we can see the microstructure. So we take 4 points, then we draw our microstructure. So the first one is on the liquid state at a high temperature around 1500 to 1060. So and then number 2 is our microstructure, which we can see contain MgCu2, which we can see that is around on the liquidus line as it on the liquidus line, so it form MgCu2. So after it cools down again, then you can see our microstructure to have a lamella on the point 3, which is around 1008 Kelvin. So as it cools down again, our microstructure, we can see at point 4, it will have a lamella structure of copper and MgCu2 and also a eutectic MgCu2. So the next is the cooling curve for our 30% copper, hyper-eutectic composition. So at around a high temperature, we can say around in the phase diagram around 1500 Kelvin. So as it cools down, the liquid mixture cooling, so approaching around approximately 1060 Kelvin, the MgCu2 started to form. We can see at the point around here, MgCu2 started to form. Then it cools down again, so the formation of MgCu2 and around at the solidus line around 1008 Kelvin. So the as is on the solid, when it approach the solidus line, the eutectic of the microstructure eutectic started to freezing. Then when it passed the solidus line, the solid mixture will be freezing. So the phases, the composition can be seen under the graph, under the cooling curve. So lastly, next is the composition calculation. So for us to calculate our composition, we first need to do our Thailand. So we take that at 700 Kelvin. So we can see at the right, you can see our Cu FCC have 96% of copper and 4% of Mg. While on the right, we have a composition of MgCu2 is 66% copper and 34% Mg. So from this, we can calculate our composition of Cu and our composition of MgCu2. We take that from the formula of A over A plus B times 100%. So we can, so this one for MCU, we calculate that 4, which is here, over 27. 27 is our distance, our Thailand distance, plus 4 here, and times 100, we get 12.9. And we do the same for our MgCu2, so we get 87.1%.
Solidification at 40% Cu, hypoeutectic composition. MgCu alloy are cooled from a liquid state from high temperature. As the temperature decreases and approaching the liquidus line approximately at 1060 Kelvin, MgCu2 started to form. Passing the liquidus line, the solidification entered the region of liquid plus MgCu2 as it cooled down from point 1060 Kelvin. As the temperature approaching solidus line, Mg2Cu start to form in the microstructure, becoming liquid plus MgCu2 plus Mg2uCu. After the 823 Kelvin, the eutectic start to freeze, then continue to solidify, forming the region MgCu2 plus Mg2Cu. Microstructure at 40% Cu. First, at point 1, we have microstructure that is only liquid. At point 2, approximately at 1060 Kelvin, the MgCu2 started to form. At point 3, at nearly 823 Kelvin, the microstructure become liquid plus MgCu2 plus Mg2Cu. After the 823 Kelvin, the eutectic start to freeze and then continue to solidify, forming region MgCu2 plus Mg2Cu. The cooling curve for 40% Cu. At first, as we said at the microstructure, the line started at high temperature, then it cools in a liquid state at approximately 1030 Kelvin. Then it starts to melt down to 823 Kelvin at the region of liquid plus MgCu2. Then it goes in a constant line at the region of liquid plus MgCu2 plus Mg2Cu. Then it goes again in melting down linearly MgCu2 plus Mg2Cu. The composition. So at first, at the composition, we chose this part at 700 Kelvin. The composition of Mg2Cu was 67% Mg and 33% Cu, and the composition of MgCu2 was 55% Mg and 65% Cu. So after the calculations of MgCu2 was 79.41%, then the calculations of Mg2Cu was 20.59% to form 100% at the final state.
The solidification at 94% copper is as follows. MgCu alloy are cooled from a liquid state until it reaches the liquidus line here, where we can see Mg will start to form in the microstructure. Upon more cooling, it will reach the solidus line, which is at 760 Kelvin, where a lamellar structure of MgHCP plus Mg2Cu will start to form alongside the primary Mg from before. After cooling past the solidus line, the majority of the microstructure will become a lamellar structure with some pockets of Mg exist in the solid mixture. So the microstructure is as follows. At point 1, you can see the majority is liquid MgCu. At point 2, upon reaching the liquidus line, you will start to see Mg will start to form, but the majority is still in liquid. At point 3, a lamellar structure of MgHCP plus Mg2Cu will start to form alongside the Mg. And then finally, upon reaching point 4, the majority will become a lamellar MgHCP plus Mg2Cu with pockets of Mg can be seen. So the cooling curve for 94% Cu is as follows. Upon reaching the liquidus line at around 900 Kelvin, the energy is used to form Mg, and then you can see upon reaching the 760 Kelvin, which is the solidus line, it will become constant here to form a lamellar structure. So the composition can be seen under the cooling curve: liquid plus magnesium liquid plus Mg2Cu, and then finally it is just Mg plus Mg2Cu. So the composition for 94% Cu is as follows. We set a tie line at 94% Cu, and then you can see that the tie line and the intermetallic Mg2Cu will be A, and then the distance between the tie line and the MgKCp will become B. So in order to get the composition of Mg, it is A over A plus B times 100%, which will get 81.82%. And then for the composition for Mg2Cu, it is B over B plus A times 100%, which is 18.18%.
As a method to improve MgCu properties, we have intermediate thermomechanical treatment. It is based on a mix of warm deformation and heat treatments, and includes recrystallization of the ingot in tiny equized grains in an intermediate stage of the working. The alloy has superior ductility, toughness, and stress corrosion characteristics for a given strength as a consequence of the current processing, primarily in the transverse direction. Change in the microstructure and arrangement of free space by decreasing impurities will increase strength and improve its properties.
Second one on our method to improve our alloy is by doing a precipitation hardening. So for us to improve our magnesium copper alloy, so we can do a precipitation hardening, which we need to have three requirements. The first one is a substantial maximum solubility, a solubility curve that decreases rapidly with temperature, and an alloy composition that is less than the maximum solubility. This is can be seen from our phase diagram is around 2 to 10% of copper composition.
So how does precipitation hardening help in increasing the strength of the material? Well, precipitation formed by heat treatment will impede the motion of dislocation and thus increase the strength of the alloy. This is because precipitation formed will disrupt the uniformly dispersed particle of the alloy, making dislocation harder to move through the microstructure. The precipitation will also block the movement of the dislocation. As you can see here, before the precipitation hardening, the microstructure at the dislocation can easily move through the microstructure, even though some energy is required to move past the grain boundaries. However, after precipitation hardening, it is harder for the dislocation to move through the microstructure. The precipitation, the black dot here, will block and disrupt, making the dislocation harder to move through it. However, if the procedure is sustained for a long period of time, the hardness will eventually deteriorate, resulting in overaging. So as you can see in this graph, at the minimum aging time, there is no precipitation formed in the microstructure. If we increase the aging time and we stop the process before reaching the peak age, you can see that although there are precipitation formed in the microstructure, it is small and underdeveloped, meaning that the dislocation can move through the microstructure easily, although it does block the dislocation better than when it does not have any precipitation in the microstructure. If we increase the aging time until it reaches the peak age, you can see that the size and distribution of precipitate in the microstructure is optimum, meaning that the dislocation becomes harder to move past through the microstructure. However, if we increase the aging time past the peak age, the precipitate will start to coarsening. meaning it will stick together, making the dislocation able to move around the precipitate. So thus we can see that the most optimum time to stop the process is at the peak age. So because of the increased strength and toughness of the MGCU, the application of strengthened MGCU is used in a situation or environment that requires it to have higher strength to avoid failures. Some of them includes automobile cables, contact wire for high-speed trains, and telecommunication cables. So in conclusion, we found that MgCu alloy is best used as everyday electrical wire because of its good conductivity, high melting point of 500 degrees Celsius, easy to weld, and lightweight properties. The electrical conductivity can be increased depending on the magnesium copper composition. However, through strengthening process such as precipitation hardening, the MgCu alloy can be used in situation that requires the electrical wire or cable to have higher strength, such as in mobile vehicle, contact wire for speed train, and telecommunication wire as discussed before.